The name of this video is Ampere's law. In electrostatics, we know that the electrostatic field is irrotational, which eventually in simply connected domains it means it's conservative. So this means that given any closed line gamma in integral form, the circulation of E has to be equal to 0. The rotational property of E, which is one of Maxwell's equations for the electrostatic field. In the case of the magnetic field, this is quite different. In fact, in the case of the magnetic field, we have that the circulation along any closed line gamma of B dot TDL is different than 0, which means B is non-conservative, is non-irrotational and more in general non-conservative. And what do we have on the right hand side here? We have a constant mu naught, which is called the magnetic constant, times a current I. Now note that this law is only true in magnetostatics. The previous law for B was actually true for any magnetic field, even in dynamics, whereas this one is only magnetostatics. We will need to change it in 342 eventually, when we're going to consider time-varying E and B fields. Okay, in particular, what is this I? I is actually the current linked with line gamma. The key word being linked with line gamma. We want to understand now what this word means. However, before doing that, let me write down this quantity mu naught, which is similar to epsilon naught, okay? And in fact, by no chance, epsilon is like E in Greek, and so it's the electric field. Mu is like M in Greek, so the magnetic field. So mu naught is for the magnetic field, and is equal to 4 pi times 10 to the minus 7 units in SI Henry meter minus 1. Great. So this is the magnetic constant. Great. So now that we have all that, what does it mean a link? That's the key word which we need to understand here. Okay, so in order to understand the concept of linkage, let us consider two rings. So these two rings are two lines which are oriented. For example, they are entangled in this fashion. And so this is the first ring, and this is the second ring. They are entangled, so they are connected. These two rings are said to be linked if, in order to disconnect them, to disentangle them, I need to cut at least one of them, okay? So here, obviously, they are linked because I need to cut. So need to cut one at least. This is the intuitive definition of linkage. More formally, if you want, the definition is as follows. So let's suppose that we have a line like this one, so a ring, so a line like this, which is characterized by a certain surface, let's say the one on the board, in this case, this surface here. Another line is said to be linked with this one if it intercepts this surface in one point only, so something like this. Okay, cut, and then I go to the other side, and I go back like this. Of course, this again has to be considered all oriented line. We will come back to this in a minute. More in general, as it turns out, two lines are linked if something like this happens. So if I have an odd number of cuts, so if you have, for example, something like this, so you go like this, so you cut, then you go to the bottom, and you go back up, you have another cut, then you go up again, another cut, and eventually you close up this line in this fashion. So, okay, obviously in this case, I've done an even number. So in an even number, actually is good. So we've done the opposite case. This means linked. This is non-linked. If instead of doing 4 cuts, I had 3, only 3, then again it would be linked. And you can easily understand this actually in the case of 2, which is probably the easiest one to be done. So let's do the case of 2 up here. So if I have this line here, and I cut it 2 times in this fashion, then I close it up, clearly these 2 lines are not linked, because it's like having this line here and then another line which goes in. I can of course take it outside, right, without ever cutting any of these lines. So that's why you need an odd number of intersections in order to have linkage, okay, which again is what we intuitively described up here. Great. So now that we know what linkage means formally, we need to understand a bit better what is this linked current I gamma. So what does it mean? So we need to do an example, because this line I gamma, as it turns out, is the algebraic sum of all possible currents in the system I'm considering. So usually we're considering a bunch of circuits where there are currents, okay? So I can have many of them. These currents, remember that they are due to charges that are moving. We know that charge algebraically sum, okay? So the same rule has to apply here. So what is this concept of I gamma? Okay, let's understand it by means of this simple example. So we consider one line. Let's do it, this line in blue here. So this now has to be an oriented line. So let's orient it in this fashion, counterclockwise. Okay, this line, let's call it gamma. So if this is my line gamma, and this is a possible surface which has gamma as a border, the one on the board, let's say, okay? Well, like this, let's do it in 3D. So it looks like this. So this is the surface which I'm sketching here. And so this is an oriented line. So obviously we need to define a normal unit vector here, which in this case will be according to the right-hand rule, n. It goes in this fashion, right-hand rule, okay? So we're using the right-hand rule a lot here in the case of the magnetic field. Right-hand rule means n goes up because it's oriented counterclockwise. Good. So then suppose that we have a first current, which is going to be a current here in this fashion, which cuts 1 time, so it's linked, okay? So this line we oriented, let's say, in this direction, okay? And so there is a current, so this is a line gamma 1. And let's say that there is a current I1 with the same direction as gamma 1. We'll come back when this, so the line is just a geometrical structure. I can decide the direction whatever I want. Then the current is the physical quantity. Typically, I want to choose the orientation of the geometrical entity, the line gamma 1, as the current, so that there is not a minus sign involved. I could choose gamma 1 to be opposite of I1, and then somehow this current, with respect to that orientation, it would be negative. But I don't have to do it now here. We will do this a little bit more in the case of inductance, mostly in 342. Okay, so suppose that there is another current here, also linked, so it crosses only once, and even, sorry, not number of times, okay? So this current, let's also orient it in the same direction. And this direction here, so this is gamma 2, and the current again goes as gamma 2, same direction. So this is my I2, okay? So now, how do I choose in the algebraic sum of these 2 currents, which I need to sum up here to get my overall linked current I gamma, because they are both linked, this current. So what is the total current linked with this line gamma? Well, I need to see the sign which I have when the current crosses the surface associated with this gamma. So in this case, it crosses in the opposite direction. See, down here, and here I'm going up. So obviously this current is effectively negative for this summation, whereas here the current goes up and I'm crossing in the same direction as n. So this current is actually positive. And so overall, mu naught I gamma, in this case, is the same coloring, so mu naught I gamma, the total current linked, if I call, in this case, I1 and I2 are actually positive because they have the same direction as gamma 1 and gamma 2. So I can simply say that I1 is negative, so it's minus I1 plus I2. I would change all these signs if I were, for example, to flip the orientation of gamma 1, but I don't have to do that because it makes things more complicated. So this is my algebraic sum. Okay, so now we know how to find in these more complicated scenarios, and of course I can extend this to many circuits, the right-hand side of this law, which is my fundamental law, Ampere's law, for the magnetostatic field, and let me stress that this is only in statics, okay? Only for the magnetostatic field B. In dynamics, we need to change it, and it's going to be called Maxwell-Ampere's law, okay? There will be some extra terms which will make it more complicated. For now, we stick to that. This means, to summarize this video, that the B field is not conservative, okay? This is quite different than the electrostatic field E, okay? It's non-conservative even in the simple static case. The circulation is given by the summation of all possible current linked with the line gamma on which I'm doing the circulation. Concept of linkage now I hope is clear. There is one last caveat which I need to give you, and this is that all this law should really be defined in a simply connected domain. So again, we have seen this also for this law when we wanted to show is Poincaré's lemma, if you want. So in a simply connected domain, this law means that E is conservative. Now, this is actually more important. Remember what is a simply connected domain. So a simply connected domain is something like, for example, I can have a structure like this. This is simply connected, but this one would not be simply connected, for example. If I punch a hole, this is not simply connected anymore. Now imagine that I had a current right here. So this is the trace. This is the trace in 2D of a current I. It's like, suppose that there is a wire which goes here and it goes through the board into this point and it goes out. This is my wire. And I somehow artificially cut it out. If I artificially cut it out, in this case, this what would simply mean is that in this new domain here, mu naught I gamma happens to be equal to 0 because I cut out surgically, I took away. So it's like I don't know artificially that there is no current, but actually physically there is a current. So this is obviously wrong because I choose the wrong domain. And this would simply mean that in the special domain, I kind of find a fake sort of conservative field B because I end up having that this is equal to 0, so it would be like that. But the issue is that really, you cannot absolutely define this law in a non-simply connected domain. So you cannot do it in this case here. You always need to be in a simply connected domain. So you see now, the simply connected domain actually is really important for deciding whether a field is conservative or not. Okay? And that's it.